Hello everyone. So let us begin today's session. In this session, we are going to have a quick recap or quick revision on the symmetrical fault analysis, and we will also see Fortescue theorem and the problems based on that. So in the power system, generally there are two main types of faults, and these two are symmetrical faults and unsymmetrical faults. And in the symmetrical faults, the system remains balanced and these faults are relatively rare but are the easiest to analyze. So here we will consider these symmetrical faults first, and then in the subsequent classes we will see the unsymmetrical faults. And what are the unsymmetrical faults? In this system is no longer balanced and it is very common but more difficult to analyze. And the most common type of fault on a three-phase system by far is the single line to ground fault (SLG), followed by the line-to-line faults (LL) fault, and double line to ground faults and balanced three-phase faults. So we can see that symmetrical faults, three-phase symmetrical faults are rare, but this is the most severe fault. If you compare all types of faults, then three-phase symmetrical faults are the most severe fault that are most dangerous, but it is also rare. So what is the fault analysis? Why we do the fault analysis? Vargavi, just mute yourself. Vargavi, yes, okay, thank you. If you have any question, then you can interrupt me. Otherwise, just mute yourself. So the fault currents cause equipment damage due to both thermal and mechanical process, and the goal of fault analysis are to determine the magnitude of the currents present during the fault, and these are needed because we have to find the maximum current to ensure the devices that can survive the fault, and we also have to correctly rate the size, circuit breaker size and the rating of circuit breakers, so that we have to find the maximum current during the fault, and also short circuit MVA we also need to calculate so that we can find the rating of circuit breakers. So these are the goals of fault analysis. And next we will having we need to do generator modeling. So during a fault, this is the only devices that can contribute fault current are those with energy storage. So thus the model of generators are very important since they contribute the bulk of the fault current, because whatever the fault current coming, that is this generator is only providing, the active sources are only providing. So the generators can be approximated as a constant voltage behind a time varying reactance, and this generator behavior can be divided into three different periods: transient period, and a steady state period. And the sub-transient period is very just for a few cycles, and then transient period comes that is considered as a relatively longer time than sub-transient period, and at the last a steady state period. So this is approximated a constant voltage having a time varying reactance. So we will see the what are the reactances during different periods. So these are the three different type of reactances. For the fault analysis, we can see that sub-transient reactance for the sub-transient period that include leakage leakage reactance plus armature reactance. XA is the armature reactance, XF is the field reactance, and XDW is the damper winding reactance. So for the sub-transient period, we include all these reactances, and just keep in mind that XA, XF, and XDW are all are in parallel. So you can find the equivalent reactance for the synchronous machine. And then we have the generator face the transient period. In this period, this damper winding effect goes down. So we are having this only two type of reactions present, XA and XF. So this XD dash that represents the transient reactance equals to XL plus this equivalent reactance of for parallel of armature and field reactance. And in the steady state reactance, this field reactance effect also bent. So this armature reactance only comes into the picture. So this steady state reactance, we just write it as XA plus XL. So on comparing all these reactances, we can see that steady state reactance is higher and this sub-transient reactance is maximum. That's why this current will, sorry, minimum XD double dash is minimum. That's why the current during some transient period will be maximum. So now we are going to see the problem based on this modeling of synchronous machine during faults. So the first question is that this question has been asked in GATE 2016. You also solve parallelly with me. And one more question. This is for the set 2 problem. So here, what are the things we have given? Some sub-transient reactance it is given of 0.2 per unit. So XD double dash is given as J 0.2 per unit. And here symmetrical fault is happening, that is three-phase short circuit is occurring close to the generator terminals, the ratio of initial and final values. And the synchronous reactance is the steady state reactance. So this is XD. XT is given as J 1.0 per unit. So how can you write the fault current during the initial and final values? The fault current you can write IF initial, that is you can EG the generator voltage, and this initial will be the sub transient reactance. So it will be 1 divided by J 0.2. It comes out as minus J5 per unit. And then fault current, that is the short circuit current also you can say, final value will be EG divided by XT. All are in per unit, so we have taken base value as the given parameter. So 1 divided by J1 minus J1 per unit. So therefore it is fine here in this problem, it is asked about the initial and final values. IF initial divided by IF final. So it will be minus J5 divided by minus J1. 5 will be the answer. So this is little bit simple problem. So it is for only 1 mark. Till here, is there any doubt?
Clear, sir.
Okay. So let us now come to uh, the the steps for solving the three-phase symmetrical fault. And for solving this, we need to generally find the fault current or short circuit MVA values. For that, first what we need to do, whatever the diagram we have been giving, single diagram generally they provide you with single line diagram. So first you just convert the single line diagram into the reactance diagram, and then you apply this fault current formula. Formula will be, the expression will be IF per unit is equal to EF per unit divided by X equivalent. That is the reactance between the generator and the fault occurring where, and then solve for short circuit MVA. Short circuit MVA in per unit will be IF per unit into EF per unit, and then if you want to find it in actual values, then short circuit MVA will be, it is just multiplied with three phase MVA rating. So here just we have taken, I have taken one simple problem so that you can get confidence in solving this three phase symmetrical fault analysis. So in this problem, find fault current and short circuit MVA if all the reactances are zero point 0.1 per unit at 11 kV and 50 MVA base. So here you need to find the fault current and short circuit MVA and all the reactances. That means Xg per unit is zero point 0.1. T1 means trans transformer 1 reactance is given as zero point 0.1 per unit. TL means transmission line reactance is given at zero point 0.1 per unit, and transformer 2 reactance is given as zero point 0.1 per unit. And the this fault is occurring at this load bus. We can say that it is load bus. This is a typical radial power system distribution system in which having one generator is there, then one transformer is for stepping up the voltage, and then we have transmission line, and again this transformer 2 is for stepping down the voltage to deliver the load. So here you need to find the fault current and short circuit MVA. So whatever we have written down these 3 points, we will apply here. So first we will make the reactance diagram. In this there is no problem for making reactive diagrams. All things are given simpler. So whatever this is given, it is single line diagram. So first we will make the reactance diagram. Reactance diagram, we have taken the generator and all the values are we have taken in per unit. So EF per unit. So taking base value as 11 kV. So EF per unit will be 1.0 per unit, and this generator reactance is taken as J 0.1 per unit, and transformer 1 reactance is J 0.1 per unit, and these are the buses 1, 2 and 3. So in this we can also represent. So here we will first find the equivalent reactance. Equivalent reactance will be just sum of the reactances values. So we will get J 0.4 per unit. So IF per unit will be EF per unit divided by X equivalent. So we will get minus J 2.5 per unit. You can also write it as 2.5 at the angle of minus 90° per unit. So if you find this actual value, then you need to multiply with this base value of current. Base value of current will be MVA divided by root 3 into VL. I think you all are familiar with this, how we find this base value for current. So for actual current, we multiply with per unit value with base current. So it will give you the actual current that will come as 6.56 kilo ampere. And for short circuit MVA, EF per unit is given 1.0 per unit, and IF per unit we have found out, we have to take the magnitude only. So 2.5 here comes. Then short circuit MVA per unit will be 2.5 per unit, and multiplying with this actual value, you will get the you will multiplying with this base value, you will get the actual short circuit MVA value. So it will be 125 MVA. So in this, is there any doubt? And now we will move to the problem section that has been asked in GATE. Generally in GATE, most of the problem asked from unsymmetrical fault analysis. So in this today class, we will look into the symmetrical fault analysis, because this is 1 hour class, so we cannot cover the full. But in the subsequent classes, we will see the unsymmetrical fault analysis also. So this is the problem number 2, and this is also asked in GATE 2016. 2 marks problem. From symmetrical fault analysis, I would say that most of the problem asked are of the type 1 mark, and for the symmetrical it may be both, but for symmetrical generally 1 mark problem is more asked in the exam. So this is this question is that the single line diagram of a balanced power system is shown in the figure. The voltage magnitude at the generator internal bus is constant 1.0 per unit. The per unit reactances of different components in the system are also shown in the figure. The infinite bus voltage magnitude is 1.0 per unit. This is generator internal bus. Both buses magnitude is given as, we can assume it as mod E. An infinite bus, we take it as V. It is also 1.0 per unit. A three-phase fault occurs at the middle of line 2. So here in the middle of line 2, a three-phase fault occurs. The ratio of the maximum, that is symmetrical fault, the ratio of the maximum real power that can be transferred during the pre-fault condition to the maximum real power that can transferred under the faulted condition is. So we need to find this uh, maximum real power. So you applied that formula, P is equal to EV divided by X sine delta, and for maximum value delta will be 90 degree. So you need to go apply that expression. So first we will make the reactance diagram for pre-fault condition. Pre-fault condition. So reactance diagram will be how it looks. It will be, so here this xg is j 0.2 per unit, and then this transformer 1 and transformer, sorry, line 1. So we take it as xt1 is j 0.1 per unit, and xl1 is j 0.5 per unit, and then transformer 2, and this infinite was. So there are two parallel feeders here, and transformer 2 is same value J 0.1 per unit. So, and line 2 is J 0.5 per unit. So you have to find the maximum value. So we know that power, active power flowing between the buses, it is given by the EV divided by X. X is the reactance between the buses, sine delta. So P max, how you can write? P maximum will be just delta will be 90 degrees. So EV divided by X. So in this problem, you have to find only the reactances, because magnitude of E and V both are 1. So just find this reactance between E and V. So this is, we can see that here 0 0.6 and 0 0.6 are in parallel. So whole this we can write J 0.3 per unit, and J 0.3 per unit is in series with J 0.5 per unit. So we can make the equivalent diagram for pre-fault condition, and this is J 0.5 per unit. So we can write P max, that is pre-fault EV divided by X. So E is 1.0 and V is also 1.0. X equivalent is J 0.5. So it will be minus J2 per unit. So we take here magnitude, no need to confuse. 2 per unit. Now for the fault condition, we have to make the equivalent reactance between the this generator internal bus and this infinite bus, and then we will find this maximum power that will pass through this faulted condition. So during the fault condition, during the fault condition, so it is fault is occurring between the middle of line 2. So we will just, because since it is a lumped parameter, so we distribute the, we divide it in the this into two reactances, half half. So here we can take the middle of line 2, J 0.1, J 0.5, J 0.1, J 0.25, and J 0.25, and this is J 0.2. This is not T, this is A. Now we make it more clear that how this will look like. So if you make it down, so take upper one whole like J 0.6 and we make this is like fault occurring here, so take it to the ground. And this is B. So is there any doubt till here? So what we will do, we will just convert this reactance. This is now we can say that this is delta connection. So this is J 0.6 and this is J 0.35 and this is J 0.25. So we will just make this into a star connection. A star connection will how it will look like. Take it as x1, we take it as jx1, this is take jx2 and this is jx3. So if you find this jx1, I am writing it here. So jx1 will be, I think you all of you know that how we can convert delta into star. Jx1, so we whatever the impedances just in the beside this jx1, take it into top. So it will be j 0.6 into 0.35. That are the impedances in between, means both sided impedances divided by sum of all the reactances. So it will be j 0.21 divided by 1.2. So it will be j 0.175 per unit. And now jx2 will be jx2 will be jx2 is between the reactances 0.6 and 0.25. It will be divided by 1.2. So it will be j 0.15 divided by 1.2. So equivalent will be j 0.125 per unit. And similarly jx3, x3 is between the 0.35 and 0.25 divided by 1.2. So 0.0875 divided by 1.2. So it will be J 0.0729 per unit. So this is J 0.2. Now we will make the diagram in a star connection. It will look like this, more simplified way. J 0.2. So this is J 0.175 and this reactance will be J 0.0729 and this is J 0.125. So this is V. Again, this is not proper simplify. Means we can add these two terms J 0.2 and J 0.175, right? So now we are going to add these two terms, and we will look how the system, how the reactances is looking between this generator internal bus and the infinite bus. So on making this, sorry. So this is J 0.375 adding the internal reactance to the equivalent reactance, and this is J 0.125 and this is J 0.0729. So this is E, this is V, and now we have to find the equivalent reactance with E and V, both buses. So how you, again you need to do transformation. So here this is star connection. So you again need to convert a star into delta. So we need to find this one only because this is the reactance between two buses, and after that we can find that we can apply that expression EV divided by X equivalent. So we know that how we are going to find this star into delta. So X equivalent you need to find just whatever the reactances we are having, just add the beside reactances J 0.375 plus J 0.125 and J 0.375.125 divided by opposite one J 0.0729. So this will be coming out as J 0.643. So the reactances will be 1.143 per unit. Therefore, we can write that P maximum during fault condition or faulted condition, maximum power that can flow from the generator to the infinite bus will be E into V divided by X equivalent 1.0 and 1 to 1.0. X equivalent is 1.143. So write it as in this form only 1.143. So here in this problem we have to calculate the ratio. So P maximum divided by P maximum during fault. So during before fault we can see that 2 per unit power we can pass it through, and after fault it is 1 divided by this maximum power reduces as this we know that fault is occurring. So this is obvious that during fault condition the power flowing to the generator to this infinite bus will be lower. If this maximum power is coming more than before fault, means you are doing some mistake. So just remember that this maximum power during fault it will be definitely lower down that before fault condition. So it will be 2.286 per unit. So correct answer for this Problem is that 2.286 per unit. So, so this is little bit lengthy problem, but you know that how to solve this type problem you can easily do in the exam also. And this type problem is asked in university exam also. So this is one of the means like usually asked everywhere in the university exam and most common type of problem. Hello, hello. Are you? I think a screen.
No, screen not shared, sir.
Not
Not
visible,
visible.
sir.
Y- Okay. So if it is not visual, then you can write in the chat box also, so that I can see chat box and you can speak whatever the
Sir,
feel comfortable. Yes.
answer is 2.286 per unit, sir.
Yes. Correct. Who is that? Koteswar.
Yes, sir.
Okay. Very good. Just practice more and more problem. You will get a very good mark in GATE exam also. So
Sir, I have another one doubt, sir.
yes.
Sir, could you, sir, here at the end of line 2, fault is occurred, sir. In this question, we got in middle now, sir.
Yeah.
If it got in at the end of line 2,
Yes. Okay. If the fault is occurring at the end of line 2. So in that condition, what will happen? If the fault is occurring in line 2, then there is equivalent reactance will be same. You can see that because this is infinite bus, so here voltage is maintained. So the power flowing between this E and V will be, you need to analyze that. So you are telling that this is occurring at the bus, right? Means at the end of in the at the end of line means it is occurring at the bus. So if it is occurring at the bus, this is grounded. So V magnitude will be 0. Okay. Hello, Koteswar. Hello, Koteswar. Are you able to hear me? Oh God. There is a network problem in my side. So
yes, sir, yes, sir. Sir, screen is not visible, sir.
yeah, I am sharing it. Now it is visible.
Visible.
Okay. So you are saying that fault is occurring at this line, end of line 2, correct?
Yes, sir.
So that means this infinite bus you are taking to ground, this voltage will be zero. So the power will be also zero. Because this infinite bus you are taking to ground means V magnitude will also become zero.
Sir, but line 1 will be there, no, sir, voltage.
Line was there, but at the end of line 2 means what? You are grounding it there means fault is occurring at bus. Both means whatever the power come from the generator, line 1 will also power will go into the less impedance path. That is the faulty path. That is grounded path. So both the parallel path will contribute to this grounding. So no power will flow, but all the power will go to the this ground, not pass to this load side. Infinite bus, whatever the load connected, that will not any power will come out into the picture.
Okay, sir. Okay, sir.
I think that yes, but V becomes zero also. But this infinite also, so this is infinite bus you cannot change the magnitude. This is fixed. This is like a slack bus. So infinite amount of means like very large amount of power will flow here. So you just take it this if you, this problem will see, if this type problem I will see, then I will try to uh, solve in the session. So now we will see these symmetrical components. So what are the symmetrical components? When we are having this unbalanced voltage or current, so we can convert this unbalanced voltages and currents into three sets of balanced voltage and currents. So the key idea of symmetrical component analysis is to decompose the system into three sequences of networks, that is three sets of networks, and they are balanced in nature. Positive sequence positive sequence components, negative sequence component, and zero sequence components. And the networks are then coupled only at the point of unbalance, that is the fault. The three sequence networks are known as, first one is positive sequence components, positive sequence network, second is negative sequence network, and third is zero sequence network. This is also called Fortescue theorem. And this is presented in paper by Charles L. Fortescue in 1918. It is judged as the most important power paper of the 20th century. So, so we have taken it as this positive sequence component. It is having the same sequence as the whatever we are studying. So we take this lambda as anti-clockwise as positive, and VA, VB, VC. So we write VV1, VC1 in the terms of VA1. So VB we write lambda square VA1, and lambda is represented by 1 at the angle of 120 degree. So and the negative sequence component will be just in the phase opposite, means in the place of B phase we take this C phase. So VB2 will be written as lambda VA2, VC2 will be lambda square VA2, and the zero sequence components all are in same phase, and these are of same magnitude. So VA0, VB0, VC0, you can all are equal. So all this in the positive sequence and negative sequence difference is the this phase sequence only, and all are having same voltage magnitude, and are all are apart from each other by 120 degree. So you need to just keep in mind this expression, that how you convert this sequence component to phase component, and this how you can convert the phase component to sequence component. These two expressions are very important. So now based on these two expression, based on these two conversions, we will solve problem. Third problem is that suppose currents IA, IB, and IC are a set of unbalanced current phasors in a three-phase system. The phase B0 sequence current IB0 is 0.1 at the angle of 0 degree per unit. If the phase A current IA is 1.1 at the angle of 0 degree per unit, and phase C current is IC is equal to 1 at the angle of 120 degree per unit plus 0.1 per unit, then IB in per unit is. So this is asked recently. It is asked in GATE 2021. So you just apply the expression we have just seen before. So what we have seen, IA 0, IB 0, IC 0, it will be 1 divided by 3, 1, 1, 1, 1, 1, lambda, lambda square, lambda, IA, IB, IC. So what are the given values we have? Given values are IA, B no, IA is given as 1.1 at the angle of 0 per unit, and IB we have to find, and IC it is 1 at the angle of 120 degree plus 0.1 per unit, and IB0 is also given. IB0 is 0.1 at the angle of 0 degree. So these values are given. Since IB 0 and IA 0, sorry, here I have done in mistake. IA1, IA2, correct. So we know that all the zero sequence component are equal. So IA0, IB0, IC0 will be equal. So it will be 1 divided by 3 into IA plus IB plus IC. So IA0, IB0 is given as 0.1 at the angle of 0 degree plus 1 divided by 3. IA is given as 1.1. IB we need to calculate. IC 1 at the angle of 120 degree plus 0 plus 0.1. So how IB we will get 0.3 minus 1.2 minus 1 at the angle of 0 degree. So we will get IB as minus 0.91 at the angle of 0 degree. So here we can see that no option is matching with the answer we are getting. So we have to manipulate this expression. We have to write it in different way. So we can write it in minus 120 degree or 240 degree. Both are same. So we are getting in one at the angle of 120 degree. So we have to manipulate like we have to get 240 degree. So what we can do? We can do add plus 1 and minus 1. So adding both plus 1 and minus 1, IB is equal to adding 1 and doing minus. So 1 plus 1 at the angle of 120 degree. So this will be IB is equal to 0.1 and 1 plus 1 at the angle of 120 degree what? So we know that 1 plus 120 degree plus 1 at the angle of minus 120 degree is 0. So we can write 1 plus 1 at the angle of 120 degree is equal to minus of 1 at the angle of 120 degree. So we put these values, so minus minus will become plus, so 1 at the angle of minus 120 degree. So this is the answer. Now we will match with the options, so D is the correct answer.
Sir, I don't understand one step. Can you please explain?
What are you saying?
Sir, at one point I didn't understand this step. Here you write ID is equal to 0.3 minus 1.2 minus 1 until 120. Yes, sir, that. Can you please explain how you write that step?
This one.
Because, yes, sir.
So here you have to. I did not get you. Means here minus 0.9 or
So how
minus.
you write the value of ID? Means, in the prior step you writing that 0.1 is equal to 1 by 3
Okay, okay.
within
This
bracket
one.
1.1.
Yeah. So take it 3 this
Yes,
side.
yes,
So it
yes,
will
sir.
0.3. So take it 3 this side. So it will 0.3. So 0.3 will be in the LHS side. So minus here RHS side 1 plus 1 plus 0.1. So it will be 1.2. So I will write one more step.
Oh, acha. Okay, okay, sir. Okay, okay. Oh, I understood.
This is so now we will see the next problem. Sorry, we will see the sequence impedances of transmission line. So for for the transmission line, we will see in the subsequent classes also for generators and right now we will see for this transmission line only. Since transmission lines are a static line, so both positive and negative sequence impedances will be equal. Means whatever if you change the sequence also impedance will remain same, then current flow will be equal. So the for this transmission line, the positive and negative sequence impedances are equal, and while this zero sequence impedance are higher. So this is very important. So Z1 value is jxs minus xm, and Z2 is jxs minus xm, Z0 is jxs plus 2xm. So and this there is no mutual inductance between the sequence circuits, so that is they are in decoupled form presented by network shown. And based on this sequence impedances, we know we will solve two problems. Very simple problem. These are. So this problem has asked in GATE 2018. It is 1 mark problem. So the problem is that the sequence impedance matrix of a short three-phase transmission line in phase coordinates is given as if the positive sequence impedance is 1 plus j 10 ohm and the zero sequence is 4 plus j 31 ohm, then the imaginary part of Zm in ohm is given. You have to find out. Since we are given with positive sequence impedance of transmission line, Z1 is 1 plus j 10 ohm and zero sequence is 4 plus j 3 ohm, and we know that Z1 is Zs minus Zm. You can take it as first, and Z naught is ZS plus 2 Zm. So subtracting 2 from 1, so it will be Z1 minus Z naught is equal to minus 3 Zm. So Zm will be Z1 minus Z naught divided by minus 3. So 1 plus J10 minus 4 plus J3 divided by minus 3. So it will be minus 3 minus J21 divided by minus 3. So it will be 1 plus J7.
That one minus J7, sir.
Okay. Okay, this is 31. I have taken now it is correct. 4 plus J31. Thank you. So thus the imaginary part of Zm is imaginary part of Zm is 7.00 per unit. So the correct answer is 7. So this is a very simple problem based on the sequence impedances of transmission line. And now we are going to see the last problem of today's session. And the problem is that the valid positive, negative and zero sequence impedance respectively for a 220 kV fully transposed three-phase transmission line from the given choices are. So what should be the correct option? Just anyone can explain how we are getting the answer here.
Z0 is greater than Z1, Z2, sir. Where Z1 and Z2 are equal.
Who is telling? Who is speaking?
Quotations.
Oh, very good. So this is asked recently. Get 222 one mark. So we know that Z1, we know that Z naught should be greater than Z2 and Z2 should be equal to Z1 for the transmission line. So the B option is correct. And this expression you also keep in mind. Z1, Z2. You can see the derivation of this, how this come this like. I think in traditional textbook you can find the derivation of sequence impedances for transmission line. So that's all for today's session, and in the upcoming session we will see the more problems based on this power system topics.
So,
Yeah.
sir,
Yes.
I'm having one doubt.
Yeah.
Sir, you write here like Z0 is for Z0 is greater than Z2 is equal to 7. Is this the
Yeah.
only case for line to line fault, or it is a general case for all faults in sequence integration?
These are impedance, so general case. These are
Okay,
the
sir.
general case.
Okay, sir.
Sir, another one doubt, sir.
Yes.
Sir, by taking only per unit values, we can also find if that is a LG fault or LL fault or triple L fault, sir. By comparing per unit values, Z0, Z1, Z2.
Means this I did not get your question. That is for
Uh-huh.
unsymmetrical for analysis. Na?
Yes, sir, sir. That numericals are frequently asked in state PSU, sir. That's why I'm asking.
Okay. What is the problem?
Sir, for example, x1 equal to 1.5, 0.2 per unit, sir.
Okay.
X2 equal to 0.15 per unit.
Okay.
X3 equal to 0.3 per unit. Then what is the fault appeared on the network? They asked, sir.
X3. What is X3?
0.3 per unit, sir.
So X3 is X1. This is
X
generally
naught, X naught, sir. X naught, X naught.
X naught. So for LG fault, we will see the expression that I have not discussed. So I will discuss because for unsymmetrical fault analysis, for LG fault, LL fault, LLG fault, we have different expression. We will all derive that. How we will make the equivalent impedance diagram for LG fault, LL fault, LLG fault. But for symmetrical fault, these are balanced fault. So you need to go through these steps only. But for
Okay, sir.
unsymmetrical fault, you need to make the different reactance diagram, right? This one, this is for symmetrical fault. This is the same for every type of symmetrical, because symmetrical fault is triple or triple LG fault only. But for unsymmetrical fault, we have different expression for fault current. It means that we have different expression for how we are going to make the reactance diagram. So we will see in the unsymmetrical fault analysis. In this chapter, I have discussed only symmetrical fault analysis, and in the last, I have discussed the symmetrical components. Because before we discuss this unsymmetrical fault analysis, you should know that how this unbalanced voltage and currents we can convert into three sets of balanced voltage and currents. So you are telling for LG and LL and double LG fault. So these are
Ah, yes, sir.
different expression. Means in general, I could tell you that for whenever ground is not there, this zero sequence reactance will not come in the expression. This x1 and x2 will come into the expression only. Okay.
Okay, okay, sir.
So we will
Sir,
see
for this,
we will see that
which textbook we can recommend, sir? Standard textbook.
a standard textbooks you go through the NPTEL lectures, and a standard textbooks you Kundru book is also very nice. NPTEL lecture you can go through this. What is the name? Power
So
system and
faculty name, sir.
power system analysis.
Okay, sir.
I will tell you the means whatever the textbook you can refer. But Kundru book is also very nice. That is advanced level.
Okay, sir.
Okay, that's all. Thank you for joining. We will see you all in the next session.